Hello, everyone. Welcome back. And welcome to this session. This is a session that's organized by Shenjun Yao from East China Normal University and Xiao Wang from the University of Toronto. And they have invited a couple of speakers that they themselves will then introduce for you. So, Shenjun, my colleague also in organizing this symposium, I will now give the word to you.
Okay, thank you for joining us. First, I'd like to introduce Dr. Zhai Wang. He will chair the first two presentations. Please, thank you. Dr. Wang, please.
Hello, everyone. My name is Xiao Huang, and thank you, Shenjun, for your introduction, and thank you, everyone, for organizing this. We are so excited to have these sessions. It's our honor to invite 5 speakers from different parts of the world. Some are from industrial, some are famous professors from the academic. So due to the limited time, we have 5 presenters. So each presenters will present for about 12 minutes, followed by 3 minutes of Q&As. So we have to move fast. So let's now invite our second presenter, Daniel Fuller.
Hello, everyone. I think you can hear me.
The stage is yours, Daniel, and we can hear you, no problem.
Great. Thank you very much. I'm going to be presenting on comparing location data from smartphone and dedicated GPS devices. Implications, I say for health research because I'm a health researcher, but also all other kinds of research. So this work sort of motivated by the question of if you're starting a study and you're going to be collecting location data, should you choose a dedicated GPS or location data collection device, or should you use participant smartphones? There's pros and cons to each of those, and I'm sure people in the audience are well aware of those. In terms of research comparing the locations from dedicated GPS devices and smartphones, there's not very much sort of naturalistic analysis or comparisons between these types of location data collection methods. Most of them involve pretty small samples, like less than 20 people. They're for specific activities like sports or transportation behaviors, and there's only a small number of different smartphones. So usually people give people the phones. So our question was, our goals were to compare the location data from a dedicated GPS device with location data from smartphones, and to examine similarities between these location measures and common indicators of environmental exposure. So these are things like convex hulls and activity spaces, broadly speaking. We'll get into that. So this work is part of the INTERACT study. So INTERACT stands for Interventions, Equity, and Action in Cities team. It's a large cohort study in Canada that's taking place in Victoria, British Columbia, Vancouver, British Columbia, Saskatoon, Saskatchewan, that's where I am, and in Montreal, Quebec. So the purpose of INTERACT actually study is still ongoing to evaluate the impacts of these different transportation interventions, AAA cycling networks in Victoria, cycling infrastructure in Vancouver, bus rapid transit in Saskatoon, and cycling infrastructure in Montreal on physical activity, well-being, and social connectedness. For the study, we use 2 different devices. So participants have a choice. They fill out a health-related survey online, and then they can either choose to wear a SenseDoc, which is a dedicated GPS and accelerometry device for 10 days that they wear on the hip, or they can choose to download the Ethica app, which is now called Avicenna, which is a white label smartphone app for data collection in research studies. So participants download the app on their phone, and it collects GPS accelerometer data for 30 days from their smartphone. So in order to examine the differences, we used spatial cross-correlation between the GPS points collected from the dedicated GPS device SenseDoc and the smartphone app. And we examined temporal epochs ranging from a whole day, the whole study period, which is about 10 days, 6 hours, 1 hour, 15 minutes, and down to 5 minutes, and spatial resolutions of 1 kilometer, 500 meters, 250, 125, 50, 25, and 10 meters. We also computed 5 different activity space measures, convex hulls, two standard deviation ellipse, a 500-meter circular buffer around the points, and a 500-meter radius buffer along the tracks of the participants, and compared those between the dedicated GPS device and smartphone location data. So in terms of participants, we had 337 participants with both Ethica data and SenStock data for the same time period. So for Montreal, we had 149, Saskatoon 59, Vancouver 58, and Victoria 71. On average for participants, we had 8 days and 21 hours, almost 9 days of GPS and accelerometer, or location data, I guess, GPS and accelerometer data for the participants. And the total analytic data set for Ethica, we had about 15,000 location points per participant. And for SenStock, the dedicated GPS device, we had just under 200,000 location points per participant. So just in terms of the participant demographics, you can see here the sample tended to be overrepresented of women, and the sample tended to be relatively older. In Vancouver, they're on average 56 years old. So in Montreal, we had a median number of GPS fixes of 8,000, and it sort of varies a little bit by city. And for SenStock, we had median GPS fixes of between 175,000 and 250,000. Oh, am I going backwards? Okay, just to give you a sense of the analysis. So spatial cross correlation values, and I'll show a figure in a second. So for the spatial cross correlation analysis, the spatial cross correlation values at 125 meter resolution, for the entire time period, and the day levels were 0.92 and 0.81, and the correlation values improved as the cell size improved. So as you go to a bigger spatial resolution, you get better correlation, and as you go to a bigger temporal resolution, you get better correlations. But the cross correlation begins to degrade below spatial resolution of 125 meters or timescales shorter than a day. For timescales less than 6 hours, the average cross correlation between these two location data sets, GPS data and smartphone data, is 0. And I'll show you a figure. So what you can see here on the x-axis is the cell size. So unless you have the cell size from 10 meters on the left of the x-axis all the way to 1,000 meters on the right of the x-axis. And then you have the epochs, which are labeled on the top of the figure. So on the top left, you have the survey, and on the bottom right, you have a 5-minute epoch. And then on the y-axis, you have the correlation coefficient. So ranging from -1 to 1, obviously. And you can see that the correlations are relatively high for the top left panel, the survey epoch, for all of the different time scales. But when we get into the 5-minute epoch, for all the time scales, the cross correlation is effectively 0. Okay, so the next thing we did was we used the data that we had, so the GPS and accelerometer data, to calculate activity spaces for the participants, and over the entire time period for the participants, and use Bland-Altman plots, which are a method for calculating agreement between two different types of variables, to examine the relationship between those 4 different activity space measures and between the 2 different data sources: GPS, dedicated GPS device locations, and smartphone locations. So SenStock-based activity spaces tended to be larger overall than the ones derived by Ethica, the smartphone app. And agreement between this activity space measures ranged quite a bit. So agreement for the convex hull activity space measure was 80%, and was as low as 54% for the 2 standard deviation ellipse, 61% for a 500-meter buffer on fixes, and 75% for a 500-meter buffer on tracks. And I'll just, again, orient you to this figure. So here on the x-axis, you have the average buffer size for the activity spaces. And on the y-axis, you have the difference in the Ethica and SenseDoc activity spaces. So if the line of agreement, the red line in the middle here, was 0, these would perfectly agree. And you can see that for example, the convex hull, on average, the disagreement is by about 43.7 kilometers. So in a relative space, it's about 80% agreement, but in an absolute space of meters or kilometers, it's quite a big difference. And there's more agreement relatively, or the space is smaller if you look at the 500-meter buffers, obviously, because they're constrained. Okay, so what does this all mean? This is, I'll just say, this paper is also published in American Journal of Epidemiology, so you can go find it there. And you can also find all the analytic code for the analysis on our GitHub page for the Interact study. But what does this all mean? So for our research, we recommend using dedicated GPS devices for studies where the exposure and outcome are measured at a high frequency and aren't aggregated. So if you are measuring something, location data at a high frequency and an outcome at a high frequency, so at the minute level or the even hour level, it's probably best to use a dedicated GPS device. But if you're measuring location at a high frequency, but then you're aggregating up to the day or the week level, the different location data collection methods provide similar results. I just want to say the Interact study as a whole is very open to collaboration and partnership. We have lots of really cool data. So if people are interested in collaborating, participating, being involved in analyzing some of these data, you can reach out to us. Find us at teaminteract.ca or socials at teaminteract.ca. Thank you, everyone.
Oh, thank you, Daniel. Thank you very much for an exciting presentation. I see there are one question in the Q&A panel. Can you switch to the panel? So, oh, there are actually 4 questions for you.
Do you want me to just go?
Yeah, if possible, can you address those questions?
Sure. The first one is, what are your aspirations for tracking devices contributing to health expectancy and life expectancy, both contributions to real actuarial science as well as consequences, including real economic cost benefits, if possible, please? Oh, there it is. Yeah, I think there's still quite a lot of work to do to understand how to measure exposures and how those contribute to health expectancy and life expectancy. We saw from the previous presentation, just measuring the exposure is already a challenging thing with GPS data, and there's not one way to do it. So I think there's quite a lot of work to do to get standardized measures of exposure that we can all agree on, which I don't think we currently have. Yeah, what about modifiable area unit problem? I mean, it's tricky to try to get away from this. I think what we see is very consistent across all of the data. So, you know, we've done 10, I don't know, I can't remember how many, 8 different spatial sizes and 8 different or 6 different time steps. And the correlations are sort of like monotonic. So they either increase the same or they're flat or they decrease. I don't think we're seeing sort of completely random correlations out of nowhere based on the testing that we've done. And the last question is the accuracy. Yeah, so a big challenge with the smartphones is people don't like the app because it kills their battery because it's collecting GPS data. So that's the main challenge, I would say, with the smartphone. People like people like wearing the dedicated GPSs. They feel like they're in a study and they're like contributing. It's not just an app on their phone that's draining their battery. So that's something that's important. Accuracy is tricky because the smartphones get location from different sources. It's not only GPS. So, you know, they're getting it from cell towers, they're getting the locations from other places, and you don't always know from the data where the fix came from, what source the fix came from. So that's a tricky problem with comparison, because that's why I was very clear to say location data rather than GPS data, because from the smartphones, you don't always know where the fix came from. And that's a tricky problem that I don't have a good answer for.
All right, thank you so much. I think you know better than me about these systems. It's working really well. Okay, so thank you again, Daniel, for your presentations. Now I have to move on, and I will hand it to Shenjun to host the rest of the presentations.
Okay, thank you, Jay. I think there is a question for Professor Ken, and let's hold the question to the end of the session, which will ensure we have enough time for the presenters. Okay, the next speaker is Alejandro, and he is an architect and MSc in City and Technology. He is now the head of innovation at Yamatech company, and he will talk about the platform they developed. Okay, the stage is yours, Alejandro.
Okay, yeah, thank you, Sachin. Share my screen. Yeah, can you see that? Yeah, brilliant.
Yeah.
Okay, well, first of all, thank you for the invitation. I think my presentation is going to be slightly different from the angle. I'm not that linked into the academic world. Well, we are a small startup in the UK, although I'm based in Spain. And I'm going to be talking more about how usually my role sits at the link between the science and the technology, and how we develop useful and meaningful applications for society. That's what our startup tries and do. And one of the key aspects is to empower those communities to make a technology that is and that spatial data science, make that accessible to the population. So I'll be covering a quick overview for you to understand a little bit more what we do. Then we'll go through the methodology we used to do in terms of empowering those communities, and then I'll talk about a few use cases. Now, the startup was born during the time of the pandemic, and we're trying to tackle the issue of people feeling lonely, the disaggregation of communities. And as you mentioned, I'm an architect. Some of us within the company, we are architects, so we look at the problems from their perspective of how we create better cities, how we become more fulfilled within our communities, etc. So one of our taglines is actually humanizing data. It's like, how do we transform the complexity and the technological advantage that sometimes is so difficult for the general population to use, to something that anyone can use and they can empower themselves to take action. So this is a dashboard that we've designed, and which is organized essentially in 3 different pillars. One is what we call Place Insight. In there, we understand everything related to the socio-demographic aspects of a place. This is for the moment, we've only developed this for the UK. The second one, we call it Walkable Cities, which is essentially POI data, but it's classified and organized in different ways, such as tackling the diversity and inclusive assets of a place, etc. And then there's a third pillar, which we call community life, which in which we collect activity. And when I say activities, I mean events and anything that can happen within a community that can make the inhabitants more fulfilled. From a yoga class to a running club, what does the community has available for you that can make you more fulfilled? So these are the 3 pillars I was mentioning, and this is just a quick visualization of that map. Ultimately, we also transform this into powerful spatial analysis that are useful for municipalities and private companies for decision making. And something really pivotal to what we do is the proximity aspect, because in many of the analysis with when understanding cities, they are being limited for the spatial boundary organization, and in our case, we use isochrones to understand the city. Let's take this as an example. Let's imagine that's a 15-minute city from any part of the country. Even within that 15-minute isochron, we can see foundational differences and really important difference between one part and other parts of the area. So in terms of socio-demographic characteristics, in terms of economic characteristics, in terms of different services of the population, etc. So what we try to do is to go to the level of granularity that is really meaningful to the street level, for people to actually take that information and feel empowered to act and change their respective neighborhoods. If I had to think about the methodology that we use, we sort of understand the objectives and goals to develop a context-based framework, depending on the vision of the local authorities or the vision of any company or client that wants to take it forward, to establish different themes and identify those key measure indicators that we want to work with. We look at those not only from the point of view of what's the status, but also what's the trend, has it changed? We are looking, for example, at an elderly population. Is that becoming a trend, or is it increasing, decreasing? What's the comparison with the district, or what's the comparison with the overall country average, etc. No? And then we actually look at those standing out values that we feel are relevant, aligned with those themes, and we present those either in a report format or through our dashboard, etc. And something, I think, what it closes that circle is actually this, for example, is a strengths and weaknesses map that we've developed for a site. It's like we looked into the different organizations in the area that are meaningful to either mitigate that gap or that weakness or leverage that strength. So it's like providing an sort of end-to-end methodology using data that the organization themselves can do something about it and can act as a change, no? And this is how it looks, the overall interface that we designed. Now, the interface, I would say, only acts as a demonstration of how that methodology can be applied into many other fields. And we've been involved in in projects related with energy, with digital inclusion, with education, so it's something that we've realized can be applied in many different areas. Now, for the sake of the presentation, I'll be going quickly through these three projects. So one is a development framework for the city. So because we are originally based in the city of Bradford in the UK, most of the projects started, and our main project started there. So you will see that the map of Bradford being appearing in the three projects. The aim of this one was to develop a growth strategy for the area. The key aspect was, let's identify, according to different indicators, which are the areas that are more suitable to impose that growth strategy. So we defined different objectives, and we collaborated also in different kind of workshops with the municipalities. So these are some of the analysis that we've developed, and we agree which one of the areas was. So it's not only using that quantitative data, but also the qualitative data from the people that live there and experience the place in first hand. So this is some of the outcome that we developed with that. And this is a demonstration of how we actually developed an interactive tool in which they could change the weight of those indicators according to their preferences. Do I want to environmental aspects to prevail with with the growth of the city, or should they be economic aspects or transport or health? So how, by changing those, they could see in real time how different parts of the city were being highlighted, and that was provoking that discussion and to take that forward. And this is some of the like summary objectives, the summary of those areas that ultimately they were taken forward by WSP, which is a big architecture and consultancy firm, and they developed on the city. The second project is a digital inclusion atlas or an index that we are currently working on. And again, it's a similar methodology to identify what's the problem. We work with the communities to identify which are the variables or indicators that might be critical to understand this phenomenon. And then we map those and create the necessary tools for one side the community and another side the council and the municipality to start to strategize action in the place. Just to finish, this is the last project I wanted to explain you about. This is something that we started doing with the Department for Education of UK, and it's called a Holiday and Food Activity Program. So the aim of this was to maximize the impact and ensure the disadvantaged children will benefit from activities. This happened because during the pandemic, children stopped going to school. So the Department for Education launched this program in which kids, so organizations will put in up activities and children could go and have fun and get some food, because there is a qualification, certain type of children that belong to marginalized families. They have they have this category of preschool meal. So we developed an entire ecosystem of applications. So we did this dashboard for the municipality. We even developed an app that geospatially the kids could see what they had around, that it was that it had that understanding of contextual and contextual characteristics of no characteristics, like more from the point of view, what do I have around me? How can I benefit from this program? And this is just some of the key figures of all the children that benefited from the program, all the activities that took place, organized by by different themes, some of the things that happened, some of the picture of those activities. And this is a report that we recently did after a few seasons, because this was happening during Christmas, Easter, and summer, and it's been happening for 3 or 4 years now. And so we were keen to understand which were the walkable limits. So each of those X's are the location of those activity providers. So we could map, which are the areas of the city that are outside this this catchment, and consequently they are left out from this program. We will do gap analysis to understand which of the regions were more benefited from the program and which ones. And all of this was was like a circular process in which we will look at this at the end of one of the program, and we will try to improve that and mitigate those gaps in the following season. We also analyzed, because we were tracking as well the attendance to these activities. So we were looking at the density of them and who. So the list that you see there are all the organizations offering activities. Who of those activities were actually putting the most, because these activities were funded by the Department of Education. So they needed to cover a minimum of activities in order to get those funding. And then ultimately also how is the participation analysis in comparison with the amount of percentage of this category of free school meals in each region, how far each children travel, and which were the areas. So the darker is the color of that grid, the further the children and their families had to travel to attend to one of those activities. And that closes this project. this is, if you like to learn more about it, we've been involved in many other projects. As I said, I'm not from the academic, and I'm not even really into the technical aspect. I'm more the guy that links that technicalities with real case applications. And yeah, I hope you enjoyed it. Thank you.
Thank you for your very interesting projects. There's one question for you from Simon. How do you know which criteria are used to validate that your app is good?
Which criteria are used to validate that your app is, in which sense? I don't understand for the question. Simon, well, can they type, or can they speak to the audience, or is it only through the chat?
I think he can be on the stage. So, can Simon be on the stage? Okay.
Well, I'll try from what I can understand. So I guess if they are trying to validate if that children is eligible for free school meal, there was a process in the app design that was exactly doing that and validating. Okay, you are from this group, then you are eligible for this. So there was a whole process of validation. If I'm not sure if that's what you mean.
Okay, thank you.
Thank you.
Let's move to the next speaker. Dr. Xiao Huang is an assistant professor in the Department of Environmental Science at Emory University. Xiao, can you hear me?
Yes, I can. Can you hear me okay?
Yes.
Okay.
Can you share your screen?
Yeah, let me try. Can you see it?
Yes, perfect.
Yeah, I'm trying to do. All right. So,
okay.
Hello, everyone. My name is Xiao Huang, and thanks for the introduction by Shenjun. I'm assistant professor at Emory Department of Environmental Sciences. And today my presentation title is, let me go back a little bit. Simulating visible greenness in urban settings. Are we there yet? So this is a small project from my team, but a really interesting one. So I decided to present it in this seminar. Before I get started, we need to understand kind of the motivation for exploring green space distribution. Green space can give us a lot of benefits, and I think everyone understands this, the importance of greenness provision pretty well. So to capture greenness distribution, traditional methods will use a top-down perspective, right? For example, one of the easiest solutions is to look at vegetation distribution from the satellite perspective, where we're using NDVI and a variety of vegetation indices to help us achieve this goal. But those methods are all from a top-down perspective, or we can say it's from a bird eye view. But humans are living inside of the cities, and we explore greenness distribution from our own eyes. So there's a tendency to look at greenness from a human-centric perspective, to explore how we experience greenness in our daily life. So many scholars have started to use street view data coupled with some segmentation approaches to explore greenness visibility in different urban settings. However, street view data are maybe only available for areas that can be reached by vehicles or personnel, and the coverage of the street view data has been a huge issue. In recent years, instead of using the street view data to get the visible greenness distribution, we started to explore human-centric greenness visibility from a simulation perspective by building kind of eyesight simulation models. The advantage of this model is notable. From a simulation model, we can acquire greenness visibility everywhere in a city. So in this study, what we're trying to do is to investigate the performance of the simulation approach. So just to give you an idea of how we calculate greenness visibility in a simulation models, If you look at this little person on the street, we first build a 3-dimensional urban model, and then we overlaid it with the greenness distribution. We then simulate the 360-degree eyesight of this person to kind of group all the land covered land use into 4 different categories: visible green, invisible green, visible non-green, and invisible non-green. And of course, the visible green is the category that we are most interested in. And some models will also consider the distance decay effect of eyesight, because human eyes are limited and we cannot see greenness miles away from us, right? So in some of the models, they will involve the distance decay function in their model. And a popular simulation model is developed by Dr. Labib in 2021, when the team actually provided an open access framework to derive greenness visibility using 3 different inputs, including digital service model, digital terrain model, and the green and non-green mask. And their method is kind of operated in the raster model by casting lines of sights at 8 different directions, and then calculating the green pixels that can be visible by people standing in the center pixel. So this is very easy to implement model, and since it's a proposal, it has been adopted by many scholars. And in this little experiment, our question is very simple. Since those simulation models have been developed in many years ago, and how do they actually perform, right? This is the question we're trying to answer. And what are the performances of the simulation models at different urban settings? So our team actually developed a evaluation framework by comparing the simulated greenness with the ground truthing data captured by panoramic pictures. We call it PGVI versus VGVI. And essentially, what we're trying to do is to investigate the consistency between the simulated greenness visibility with the pictures we've captured in different areas. We divided the entire study area into different local climate zones and generated random points, sample points, get out, and then to collect some panoramic pictures. We then segmented those pictures using some segmentation models to extract the greenness in those from those images. And finally, we compare the model simulation results with the results generated from the pictures we've collected. So our study area is in Fayetteville, Arkansas. It's a typical mid-sized city and in the United States. And it is also where University of Arkansas is located, my previous institution. You can see the local climate zone distribution in this area. Compact low-rise areas are in the center of the city, and well, the open mid-rise are kind of dominated and distributed across the space. We generated around 800 sample points in the city, and with 100 sample points corresponding to each local climate zone. And then we started to collect those panoramic pictures. And you can see my student, Jingjing Yan, collecting pictures at a sample point. She used a special camera that can capture the 360-degree view, and she mounted this camera at a stand, which is around 170 centimeters tall, which corresponding to a regular person's height. We track the sample collection process using open software, open platform, so the whole team can monitor the sample collecting process altogether. We used Deep Lab version 2 for segmentation. You can see, of course, there are many segmentation models available, but we tried all of them, and we found this model actually achieved a really good performance. So we chose it eventually. You can see from the figure that the vegetation, including grass, bushes, and trees, are kind of successfully extracted from the view. As for the simulation results, the figure on the left-hand side shows the simulated visible greenness in our index, in our study area, and the figure on the right-hand side shows the NDVI distribution in the study area. And you can clearly see some resemblance of those two indices, right? So in the general sense, a region with high NDVI represents lots of vegetation, right? And is likely to present high visibility scores, visible greenness scores. But if you look closely, you can tell that those two indices are quite different, especially in areas with buildings. So for example, in the downtown square area, we can clearly see the eyesight blocking effects right? Areas around the buildings present limited visible greenness. And by the way, the simulation runs at a resolution of 1 meter level. So it means that we have to conduct a simulation for millions of observation points in our study area. And we run the model in a very high performance computing environment but it still takes days to run the entire simulation model. As for the performance of the model, it varies. And to be honest, it does not meet my expectation. The general conclusion is we found a significant positive correlation between the simulated greenness and the ground truthing greenness from our pictures. And this significance passes the regular correlation test as well as the TOST test. But the consistency varies a lot in different urban settings. We observe a very poor correlation in the compact low-res area, but in open low-res area and open mid-res area, we observe a high consistency. So it means that for greenness simulation models, we need to pay more attention to its performance variation. And in certain urban settings, like the compact low-res area, its performance may not or fail to meet the expectation or fail to meet the requirements. We need to think about ways to improve our simulation model in the future. And quickly, just some points I want to discuss here. First, from a technical perspective, we need to acknowledge that human perceived greenness changes dramatically given different seasons in a year. And although this is not focus of the study, but we encourage future efforts to explore greenness visibility across different seasons, which is often a overlooked issue in greenness distribution visibility assessment. And high performance computing environment is another issue. Our resolution is at 1 meter level, so we have to simulate 235 million observation locations in our study area just to have the map I just presented. The simulation framework has to run in a high performance computing environment, and we're now developing strategies to kind of mitigate this computational demand. Some general discussion points. We believe that the simulated greenness visibility is a very promising index that allows greenness visibility to be calculated anywhere in the city. And in the model, we try different parameters during the simulation. So the model actually offers a lot of flexibility, allowing us to examine different scenarios. And we also believe that the simulated visibility greenness can assist urban planners or stakeholders in kind of proposing strategies to enhance the view of nature for urban residents. But we do acknowledge that there are still many unsolved issues during the simulation process. And in our article, we actually envisioned a series of potential solutions. And this article has been published in Urban Forestry, Urban Greening. So if you're interested, feel free to check the article out. And one more promotion, we are offering a new PhD program from Emory. It's called Environmental Science and Society with a 4-year guaranteed fellowship. So if you are interested or want to have more information, feel free to contact me. Thank you. And I'm really sorry for the technical issue I'm having here.
Thank you, Xiao, for the very inspiring talk. And the greenness is a very important topic. Time is limited. Let's move to Siqin. Siqin Wang is an associate professor at the Spatial Sciences University of Southern California. Hello, Siqin. The stage is yours.
Hey, hello. Yes, okay. So let me try to share screen. Take window. Okay. All right. So I'm trying to switch to the presentation mode. Is all good?
Yes, perfect.
Okay, all right. Oh, thank you very much. It's a great pleasure, even though right now it's still quite early in LA, but a great pleasure that to join this exciting event. That I also see there are many similar faces that I know. All right, so today's topic, the broad topic is about GeoAI application in human environment interaction. And so as Professor Yao just introduced, my name is Cici. I'm working as an associate professor at the Spatial Science Institute at the University of Southern California. So in the very beginning, brief introduction of my research interest. So that is integrating spatial science together with big data analytics in the particular domain of computational social science, digital health geography, and human environment interactions, or more specifically, population health and place, which is the PhD program that we are having at USC as a PhD program. So that's, again, if any one of you have the interest, welcome to apply. So very generally speaking, my interest is to look at the human side, such as how we quantify human behavior by using different types of social sensing methodology. So those are the work dramatically done by the US team and the Japan team, given I previously stayed in University of Tokyo for a fellowship for 1.5 years. And on the other side, I'm also interested to see how we use such as remote sensing to quantify environment in terms of social environment, built environment, and the natural environment. Those work are predominantly done by our Australian team, given previously, before I moving back to LA last year, I stayed and working in Australian University of Queensland for around 8 years. And then what's linking in between human and the environment side are advanced spatial modeling spatial models, or such as a GeoAI application. So that's kind of the framework that I have been studied, implemented into any of my studies. So today's talk, we narrow down into one perspective of the holistic pictures of GeoAI application in human geography. We narrow it down to by looking at the human perception of the environment. So we have done a couple of pieces of work across the different study regions, including Melbourne, Australia, and then quite recently LA County, by using computer vision and a multimodal machine learning method, trying to look at what is the relationship in between human perceived built environment vs the actual built environment. And as well as what is there any social inequality issue linking to their perceived environment. So in the very beginning, I would like to give credits to the team. So the paper that I'm going to present today with the title of Reducing Social Inequality of Neighborhood Visual Environments in LA County through Computer Vision and Multimodal Machine Learning. That is a paper currently right under the second review under Sustainable City and Society. Hopefully, we want to try to get it published pretty much shortly. And then, so if you have any questions, that you can refer to this published paper at a later stage. A brief introduction of the background in the beginning. So according to environmental psychology and well-being, so we all know that the people react differently towards the surrounding environment. So that's the theoretical background that we are basing on. So here in this particular paper, our interest is how the built environment is associated with humans' visual perception towards places as a reflection of the well-being. So let me go with the next content quickly. So data collection, we are using the street view imageries, including almost 70,000 imageries collected in the LA County, together with a 5D built environment in terms of density, diversity, the distance and destination and design. Those are based on the point of interest collected from OpenStreetMap. So that's an analytical workflow. So you will see up on the top, that's different sources of data in order to quantify the 5D built environment. And what is sitting on the bottom, so that's we are using Street View together with the training data sets coming from MIT Sensible City Lab to train our model in order to identify 6 different types of perceptions, including the feelings of beauty, safe, wealthy, boring, livable, and depression. And then to look at the relationship by using what's sitting in the middle, 6 different types of machine learning methodology, and then in order to address 2 goals. So I will add a little bit more information. So here you will see the results. So that's a perceived built environment at the point level. So that's where the imagery are collected, 6 different types. And then we further aggregate the 6 different types of human perceptions into census tract level, and as well as construct a new composite overall index. The name is Neighborhood Soundness Index, in order to represent the overall feeling of the people surrounding towards the surrounding environment. And then, so we further analyze the social inequality relating to perceived built environment across the different social groups, such as you will see the mean value of the boring and depressive feeling within the white group comparing to all other minority group are dramatically lower than those ones among the rest of the social groups. And on the other side, all the positive feelings is much higher than the other groups. So there's a very obviously we can see there's a social inequality issue involved here. And furthermore, by applying the 6 different types of machine learning methodology, we would be able to find out what is the most important built environment factors are going to matter most the human perception. So we can see what is the ranking on the top highlighted in the red box. Those are the density of the tree canopy, playing probably the most predominant role in this relationship, which is also following by different other ones. And also, if you look at the difference across the different social groups, we will also see the tree canopy plays a predominant role here, no matter which social group that you are looking at. We also break it down into the local relationship in between aesthetic diversity and the perception. We will see most of them, the positive feelings, stick a negative relationship with aesthetic diversity. However, the two positive, the two negative ones, boring and depression, they keep a positive relationship. So overall, very quick summary of the key findings. So we'll see those underserved and minority groups, we can see there is a dramatically higher level of feeling boring and depressive. And we also see the built environment factors strongly correlated with this phenomenon. They are including density of the tree canopy, density of multi-units, and distance to CBD, and the car commuting to destinations such as a working space. And we will also see the distance to the shoreline, the ocean, Pacific shoreline, also has a dramatic impact on the neighborhood soundness level, and as well as the distance to the commercial places. All right. We also provide a very nuanced policy implication, which I don't have time to introduce here, but welcome to read our paper once it's published. All right. So that's all. Thank you.
Thank you so much, and thank you all for joining us. And now time is up, and we can continue chat on the chat room. Okay, thank you.
Nicht schlecht, in time.
Thank you.
Okay, thank you so much.
Thanks. And after the break, we'll continue with the early career session. Bye.
Bye. Bye. Thank you.
Bye-bye.
Bye. Bye. Thank you.